Welcome to this introduction to electricity. Electricity, the movement of electrons, basically comes down to that. We need electrons to move, and bingo, you have electricity. So let's start at the beginning. Elements. The elements are the simplest form of any matter, and when you take those elements and you break them all the way down into their smallest little bit and pieces that are still have all the characteristics of those elements, you have an atom. And here's the periodic table of the elements, all 118 of them. And so let's take a look at our atom. This is a model of an atom. Of course, it's not to scale. The nucleus has 90% of all the mass of an atom, but it's much, much, much smaller than the overall size of the atom. 90% of the mass, but only less than 10% of the area. So that's the center portion of our atom. That's where we're going to store our protons and our neutrons. So what are these protons? Well, these are positively charged atomic particles. Of course, they're accompanied by the neutrons, which are uncharged atomic particles. So the atomic number of an atom is based on the number of protons that are in the nucleus. So here we have a nice little atom. If we dull the neutrons, you can only see the protons. How many are there? What would be the atomic number? Next, we want to talk about the electrons. The electrons, mass-wise, are teeny, teeny, teeny. But charge-wise, they have exactly the same charge as a proton. But it's the exact opposite charge. Whereas protons are positive, electrons are negative. And they don't live in the nucleus. They live in the surrounding regions. And we call them orbitals or energy levels or orbits or shells, and we have several different names for them. Electron orbitals are where we're going to find these electrons, and we usually draw them in a more simpler pattern, something like this. And we can see this has 2 in the inner shell and 2 in the outer shell. And that's going to be important when we talk about electricity. Where are those electrons? And that's why we're going to especially pay attention to the valence electrons. These are the electrons in the outermost ring. See, protons, they're in the inner nucleus. They're not really going anywhere in your typical atom. They're really tightly, tightly held in there, and that's not what's moving. The charge that's moving to form electricity is electrons. And so that's why we have to pay special attention to how many they are and where they are. So let's take a look at a typical metal element like copper. Copper is an important element when we're talking about electricity. So let's take a look at the electrons, because atoms, when they're filled, they're usually going to have 8 in the valence. And when they're empty, they'll have 0. So copper here, we can see it has 2 in its inner shell, has 8 in the next shell, 18 in the following shell, and that brings us to 28. Well, there's 29 electrons, so there's 1 electron left over in that outer valence shell. So this configuration that we're seeing here, this is based on the pattern, the energy levels that we find electrons in. This goes to the shape and the patterns of the periodic table also. But we're not going to get deeply into that because we're mainly interested in the valence electrons. Well, like I said, we have 1 valence electron right there. And so, question, is copper a good conductor or is it a good insulator? Well, we pretty much know that it's a good conductor. So the question comes to why? Why is it a good conductor? So think about that for a moment. We'll get back to that. How about sulfur? Let's take a look at sulfur. Sulfur has atomic number of 16. So we have that same pattern of 2 in the inner shell, 8 in the next shell. But instead of 18, we have 6 in the outer valence. That's how many is left over. And at 6, well, 6 is pretty stable. All right, it's a pretty stable situation. Sulfur is pretty happy with 6 electrons in its outer shell. And if you're not familiar with sulfur, sulfur is not a good conductor. It's an insulator. So again, why? Well, kind of give you a little hint there already. We need to talk about that. Why is one a good conductor and why is one a good insulator? First off, let's take a look at what's going on. Remember, electricity is about the movement of charges, or for us, that means electrons. The electrons need to flow. So here's copper again with just that one electron in its valence. If another electron comes along, it might knock that electron out of place and take its place, and off goes that electron. That is a movement of charges, right? Charges are moving from one atom to another atom. So let's take a look at a string of atoms here. Here we have 4 coppers in a row. If we notice, the first one is missing its outer electron. We'll need to give it one. And here's the outer electron here, and of course the other one has one too. So let's take a look at what would happen if the electrons interacted with each of these atoms. So there's an electron, boom, 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 right? So that electron is going to move from one atom to the next atom to the next atom. This movement that easily, freely happens with copper is why copper is such a good conductor. The movement of charge, the movement of the electrons. So let's take a look at what kind of characteristics do we see with really good conductors, and what characteristics do we see with elements that are good insulators. Well, conductors, their electrons flow very, very easily from one atom to the next, to the next, to the next. Very important for a conductor. Insulators, not so. They're more stable. They're very happy with the number of valence electrons that they have, and so the electrons don't flow from atom to atom to atom. Conductors, we find that they tend to have 1 to 3 valence electrons in their outer orbit. Insulators, usually 5 to 8 electrons in their outer orbit. Now you might be thinking, well, what happens when you're at 4, right? You're not 3, so you're not a good conductor, but you're not 5, 6, 7, 8, so you're not a good insulator. Well, these are semiconductors, and you've heard about semiconductors, and that's an important topic for another conversation. Well, what are good conductors? Well, silver, copper, gold, aluminum. These are all excellent conductors, among others. Insulators, mica, glass, quartz, and several others all make up good insulators. So take a look at this picture. Do you see any conductors in this little photo here? Well, immediately you should have thought of, well, what about that? That's metal. That should be a good conductor. And what about those little copper wires there? Those must be good conductors also. And you're right, they all are. What about insulators? Do you see any insulators in this picture? Well, all those little copper wires have a sheathing around them. The sheathing's there to act as an insulator, right? To keep any charges strained from wire to wire to wire. But also those little pliers there, those needle nose pliers, they also have insulated handles. So if you're working with electricity, the charge isn't transferred from the components you're working on into your hand, because that would be shocking, right? All right, so let's get deeper into electrical circuits. But before we do, we have to have some terminology, some terms that we can use to understand what's going on. So voltage, current, and resistance are the concepts we want to talk about. Voltage is measured in volts, symbol is V. Current is measured in amps, symbol is a capital A, named after Ampere. Volts gets a capital V because it was named after a person also. And resistance is measured in ohms, and it gets the capital omega symbol for ohms. So a good analogy for electrical circuit is a big, huge tank of water with a pipe and a spigot. So that big tank of water, that's like our battery. That's our reserve, right? We're going to pile up a bunch of water in there. We could make it deep, we could make it shallow, but that's our reserve. The pipe is like our wiring. The pipe is what our water is going to flow through, correct? Just like the current needs to flow, right? Our charges need to flow to create current. And then, of course, we have our faucet, which is like a switch in our electrical circuit. So, at the moment, switch is off. Is there any current? Well, no. The water's just sitting in the pipe. It's not flowing. Or the analogy being the charge is not moving. So, no, there's no current. But if we turn that spigot, we create a current, now we have flow, right? So, and of course, this is going to drain our tank, just like we would when we turn on a switch, we drain our battery. So here we have a little circuit. We have our nice little battery here, got a positive side, a negative side. We have a switch, it's in the off position, and we have a lamp, and oh, it's so sad, the lamp is not shining. What can we do about that? Well, when the switch is off, just like when we turn off the spigot, no flow, no current, and therefore it's not doing any work. This current cannot do work on that lamp and produce any light. But if we turn the switch on, bada bing, bada boom, we get light. And now there's a flow of charge in this circuit, moving around and around and around. And as it passes through this lamp, light is produced. And we're able to do work with that current flow. So what about current flow? If you notice in that previous diagram, the current was flowing from the positive to the negative. This is the conventional way that we demonstrate current, and the way we're going to demonstrate it in our class. But current flow is the flow of charges, and the charges that are moving, they're electrons, right? So if they're electrons, they should be moving from the negative side, and that is true. The electrons do move from the negative side. They travel around the circuit and come back to the positive side. Well, that's curious. If the electrons are flowing from the negative around to the positive, why do we say that current goes from the positive around to the negative? Well, it's a matter of convention. All right, this is the way it was set up long ago, and you might want to think about it as vacancies. All right, you can't move, right? The electron can't move from one place to another unless a vacancy opens up, right? When you move out of the home of your parents and you want to move into your first apartment, you can't do it unless there's a vacancy to move into. So while the electrons are flowing around the circuit in one direction, the vacancies, the spots that they're moving into, they have to move in the other direction. So who was it that came up with all of this? You know, who was it that long ago came up with the fact that, or the idea that current is flowing from the positive to the negative? Well, you remember good old Benjamin Franklin. He was that guy, the crazy guy who went out and flew a kite in the storm. He wanted to prove that lightning and electricity were related concepts. Well, he back then, not in this experiment, but in a different experiment, decided that the side that had an excess flow of charge must be positive, and the side that had a negative or deficient flow of charge was the negative side. And so he came up with the terminology and decided on the current flowing from positive to negative. And we've just stuck with that. All right. So good old Benjamin Franklin, he was the one that discovered this among many other things. And so it is the way it is. So that's the way we're going to be labeling it. In a physics class, we might spend more time talking about electrons and the flow of electrons. But even in physics class, and certainly in engineering, we like to say that we stick with the idea that current flows from the positive around our circuit and back to the negative. So when you identify current, that's the way you should do it from now on. So let's go back to our tank. All right, our tank, because it has this water in it, it's creating the pressure. And the pressure is, of course, force divided by area. So this is the force that gets the water moving. The deeper that tank is, the greater that pressure is going to be. And this is a great model, a great correlation to the concept of volts. The deeper this tank is, the greater the amount of volt or voltage that we'll experience in this tank slash battery. All right. And of course, when the faucet's off, is there still voltage? Well, yeah, the tank is still deep, right? It still has water in it, and that water is going to stay there. When that switch, as long as that switch stays off, we should, unless there's evaporation or something like that, we're going to keep having a reserve, a voltage, a pressure, a force in that tank. Okay. As soon as the pressure is turned on, is there still voltage? Well, yeah, there's still voltage, but that voltage is, of course, going to drop over time because of the flow of current. And that's what we see when we use a battery and we hook up a light bulb to it and we turn the switch on, that battery is going to lose voltage over time. And so we take a look here, and here's our circuit, and we flick the switch, and the light lights up. Very good. Because there is a voltage, there's a force that is pushing those charges through that circuit and back to the other side. Now, what about resistance? Sometimes we have a resistance. This pipe might have corrosion in it that would slow down the flow of water. We would get a laminar flow. We have a faucet here that might have some constriction, some smaller areas and orifices in here that will slow down the flow of the water. This is resistance. Okay? So let's be extreme. Let's say some crazy person threw a rock into our tank. Why, how dare they do that? And it gets sucked into the pipe and goes all the way down to our faucet or our switch. What's going to happen? If you said the flow is going to decrease, then you're right. The flow is going to decrease because of the increase in resistance to the flow of our water. So you might be thinking, well, that's a horrible thing. We never ever want that to happen. Sometimes we do. We do put resistors in our circuits to serve purposes. It might be to keep from blowing out a component like an LED. An LED might not be able to handle the same amount of voltage or the same current flow that another component in the circuit, in that circuit or a parallel circuit, can handle. So you need a resistor to solve that. So for now, let's go ahead and put a resistor as a component right here in our circuit. So we add the resistor, and what's going to happen to our light bulb? It's going to get dimmer. That resistor is going to reduce the amount of current that can flow through our circuit, and when you reduce the current flow, you reduce the amount of work that current can accomplish, and the light bulb gets dimmer because we reduce the power. So in the lab, to measure voltage, we're going to be using a device that looks something like this. This is called a multimeter. Multi because it measures a lot more than just voltage. It's able to measure quite a few different things for us, different concepts that we can test with it. So here we have a simple circuit, battery, switch, resistor, and a little LED light. Now, if we want to first we have to set the multimeter to the proper voltage range. Right here, we can see that there's voltage V, DC. That's what we're interested in. Over here, this is AC. AC is the type of current, it's called alternating current, that you get from the socket of your home or in the lab. The wall sockets produce AC current. It's an alternating current. It flows one direction and then it flows back the other direction. It's a little bit more complicated than what we want to get into at the moment. We're going to stick with DC. Batteries are DC. And most of the components that you're interested in, your phone, your computers, and a lot of other components do run on DC. We plug them into the wall, and then we go from AC back to DC to run our components. We've identified the positive side of this battery. We've identified the flow of the current. We've set the voltage meter to 20 volts. That's an appropriate range. This is a 9-volt battery here, and you can see that this is 2,000 millivolts or 20 volts. So 20 volts would be an appropriate number for the maximum range to measure something like a 9-volt battery. All right, so that we zoomed in there so you can see that it's set at, see the little line right there? Sometimes students will focus on this end of the switch. And so they think, oh, look, I'll switch it to 9 volts. Well, this is for battery testing. All right, so this isn't going to actually give you a voltage reading. It's going to give you a different kind of reading. to tell you whether that 9-volt battery is any good or not. All right, so let's measure across a component. So you can see that we have the red end of the multimeter probe on the positive side and the black on the negative side. All right, and that's going to be the way it's going to be. The red one should always go towards the positive. If you switch them, you'll get a negative reading up here. And so you just know to switch them back. It won't damage the multimeter, but that'll prevent you from getting a negative reading, and you'll end up with a positive reading. And all your measurements will be a lot more consistent that way. So you're not subtracting things when everything should be added, for example. So you measure across there, and then we could measure across the switch. Notice the red is towards the positive, the black is towards the negative side of the circuit. Then we can measure across the resistor. Now, of course, this is just showing it touching the wires. We would not be touching where there's insulation. We would want the metal conductor of the probe touching the metal conductor of the resistor, and so forth, and also with the switch and with the battery. And then, of course, then we can move it over to the light and measure the voltage across the light. So this is a way to measure the voltage drop, to measure the voltage reading for every single one of these components. All right, which is it's an important test. Here's shows several different multimeters. This multimeter looks like the ones we have in our engineering lab. We have this model, and we have others that are very, very similar to it. And we can use it for measuring, again, voltage, current, resistor, resistance, and of course checking batteries. We can check continuity. They're really very useful, very versatile. So what about measuring current? Current's just a little bit different. We need, when we measure the current, we need the current to flow through the multimeter and only the multimeter, right? So to do that, we're going to set it to amps DC, and you can see here we have it at 20 milliamps because this battery can't produce major amounts of amperage. But you notice this is 2,000 microamps, 20 milliamps, and 200 milliamps. These are not a lot of amps. This unit couldn't handle too many amps running through it like this. So we're going to take the component out and replace it with the probes of our multimeter. So this way the current has to flow through the multimeter from the switch to the resistor. And then we could do the same thing again from point to point. So what about measuring resistance? Well, if we just put the resistor on this circuit, let's say from one side of the switch to another, we're not just measuring the resistance across the switch, we're measuring the resistance of the entire circuit, including the battery, which isn't really what we want to measure. So that's not a good way to measure this resistor, for example. So we need to take the battery out of the circuit. So you can see on our multimeter, here's the omega symbol for ohms, and we're setting it currently at 20,000 ohms. It can be moved from one to the other as needed. So we're going to measure across the component being tested, and again, the power, or in this case the battery, needs to be removed. And when we look at our meter, you can see it looks very different. It has a 1 over here and nothing else. Well, this means infinity. This means that there's infinite amount of resistance. Basically, right now you're measuring the resistance of air. How much current is flowing through the air? Or what's the resistance to current flowing through the air? Well, it's an infinite amount of resistance. So that's what that's trying to tell you. The LCD isn't set up for showing the infinity symbol. So we remove our battery, and now we can put our probes across the switch. And when the switch is off, it's going to stay infinite. When the switch is on, it's going to be quite a bit lower. We can measure across our resistor. We can measure across our light and find out what the resistance is there. Lamps are, now this is an LED light, but incandescent lights are resistors. LED lights are diodes, which we'll talk about in a different presentation. All right, thank you very much for viewing Introduction to Electricity Part 1.